So hello again. Tonight we're going to talk about very low Earth orbit, or we'll actually get lower than VLEO. How low can you go kind of thing. So everyone knows about satellites and they orbit the Earth, and there are different bands, different altitudes where you have different kinds of satellites doing different things at different orbital altitudes. You have the acronyms there on the left. You have high Earth orbit. That's actually higher than geosynchronous or geostationary. And that's useful for seeing like an entire half of the Earth at one time. So you're getting a broader view. Then you have the one geostationary or geosynchronous. And the difference between those is if you're at an orbital distance sufficient that the place on the Earth that you're above stays the same because your orbital period is an Earth's day. Oh, that's wrong. It says 25 hours, should be 23 hours, 56 minutes, 4.09 seconds. Anyway, that's geostationary versus geosynchronous, because you can have a tilted orbit, tilted 90 degrees, and that's called a sun synchronous orbit, where you're going around the Earth once every 24 hours as the Earth is turning underneath you. So you can make this like striped pattern of observations, and in 24 hours you do like one Earth orbit. Then you want it to be lower altitude because it takes less fuel, less rocket to get you there, but you want it to be up high enough where you cover a large enough area to make it worth your while. You don't have to have as many satellites. This is where medium Earth orbit is. This is where the GPS, GNSS, all of the navigational satellites are at. They want their orbital period to be 1/2 of an Earth day, not an Earth day, a sidereal day. And that comes into play as three-dimensional triangulation with the Earth rotating beneath you. And there in the rightmost column, you can also see the orbital speed. I would say velocity, but the velocity is constantly changing. So it's actually orbital acceleration, not velocity. So we'll just say speed. Because speed is just how fast you're going, not what direction you're going. Lower than MEO, lower than medium Earth orbit, is low Earth orbit. Now, you probably have heard of low Earth orbit in relationship to constellation satellites. These are low enough that the orbit of one satellite takes about 2 hours. And if you put enough of them in orbit, you can have a satellite going overhead, crisscrossing wherever you are on Earth about every 18 minutes with an overlap of 2 satellites. So you literally have an 8-minute duration of one of 2 satellites anywhere on the planet. And they put up enough of them in orbit. That includes Antarctica. So by having several thousand in orbit at the same time, at different altitudes, at different inclinations, you have complete global coverage to the point where they're close enough that the transmission delay is about what a long duration cell tower might be out in the Midwest somewhere. They're now making it where the constellation satellites can also operate not only on their own private frequencies, but also on the public wireless frequencies used by AT&T, Verizon, and T-Mobile. So you can be out in the middle of nowhere. You can be in the Antarctic and get cell phone coverage courtesy of Starlink. But you got to have a Starlink account. Turns out there's an even lower orbit. If you want to use a small rocket, it's not going to get you up to one of these higher orbits. So you'll be in very low Earth orbit. As you can see, every 24 minutes you're very fast. Every 24 minutes, you'll make an orbit of the Earth. You're about 250 miles up. But these kind of orbits may be useful because the communication delay is low. It costs less to put them up there, but there's different altitudes for different purposes. The most interesting one is one that Helen introduced me to years ago called a Molnia. Imagine you're in Russia. You're at very high latitude. You can't look down far enough to see geostationary satellites because they're going to be along the equator. They're going to be on a stationary slot along the equator. So if you look in South Florida, your DirecTV satellite dish is fairly low. You know, it's not like overhead, it's fairly low. If you're in Russia, it would have to be pointed down so low to the horizon that the sun would interfere with it certain days of the year. So what they do is they put up several satellites, and they're on very long elliptical orbits. So they go slower as they go higher, and then they go faster as they come in lower. So they're on a very elongated egg-shaped orbit. And when you put up multiple of them at different inclinations, you can now ensure that there's always going to be one of them going over at a slower speed, your high latitude city position. This is how Russia's data communications and TV communication satellites work, is they're all Molnias. But they're useful for other things too. That's Molnias looking down. Having a Molnia looking out. And if you want to get out away from the Earth's light, electromagnetic fields and such, and you want to look at something in space at high resolution, you don't have to send it all the way out to Lagrange point 2. You can just put it in a Molnia orbit where the perigee, where the close end of it, goes right over the California Deep Space Network radio antenna. So it goes way out over Europe, way at a high peak altitude, and it can point out to space, but it's at such an inclination that the Earth rotates with it. So that's how the Transiting Exoplanet Survey Telescope TESS works. It's got a Molnia orbit, and the perigee is over the Goldstone Deep Space Network, and the distant one, it points outward and it rotates with the Earth. So every orbit, it can look at a different part of the sky. But since it takes a long time, like every 13 and a half so many days for one orbit. Also, when it's nearby, it's a fraction of a second to communicate with the satellite over Goldstone. But when it's that far away and it's on the other side of the Earth, it could take more than a second to talk to the satellite because it's that far away from the Earth. It's farther away from the Earth than the moon. Geostationary, we know that for communication satellite, but they're typically along the equator. Medium orbit, those GPS satellites. Low Earth orbit, those are the constellation satellites. And we're not going to talk about all the other fancier orbits that have different inclinations or eccentricities. They're just variations on these satellite orbits. So being at very low Earth orbit has benefits. It's faster moving. You get multiple observations per day. Fast orbital period, a couple of hours. Being lower, it takes less fuel to get you up there. A smaller rocket, cheaper to launch, can launch them more often. You can launch these cube satellites and microsatellites up there. But at that low in orbit, you still have some amount of the atmosphere left. So there's drag. And they refer to this as it's a self-cleaning orbit. Because if you launch something up to very low Earth orbit and you don't do anything to keep it up there, like propulse it up occasionally, then not too long, it will fall back all by itself. It will fall back all by itself and burn up. So if you want it to last longer, you have to have some kind of propulsion, and now you're left with other issues. But this is why they refer to it as self-cleaning, because you're down low enough, the atmospheric drag will eventually drag you back down and you'll burn up, hopefully in a controlled V orbit. You're not going to land on somebody's house, so to speak. So how do they keep them up there? Well, most of these satellites have a fixed at time of launch fuel tank. And the really big satellites that they have up at geostationary, they tend to have big fuel tanks because they need to move big things and keep them at the right distance and at the right slot along the equator. So when their fuel tank is exhausted, they move them over a dead part of geostationary orbit, usually over the Pacific Ocean, because there's lots of spare slots with nobody below it. So that's how they make the geostationary satellites deal with their lifespan, which is usually 20 years or so. The lower Earth orbiting ones, they need more fuel for this. This is why they usually give them about a 5-year lifespan. Even the ones with ion thrusters that use xenon or krypton or even argon gas. The Starlink satellites use ion thrusters because that allows them to not run out of fuel for about 5 or so years. The very low Earth orbiting satellites, if they don't have some kind of propulsion, may only last weeks to months. And if you think, well, we'll just put out solar panels and that's how we'll get our power. The amount of atmosphere is so high and the drag is so great, you cannot put out solar panels because they'll act like giant wind sails in the atmosphere and drag you down quicker. VLEO satellites normally have the solar panels built into the exterior of the spacecraft. If you remember the old Telstar, the sphere that had all like the hexagonal panels on the outside, and the solar cells were actually built into the outside of the spacecraft. So VLEO satellites with solar panels have the panels built into the craft so as not to stick out and increase the drag. So whenever you launch a rocket that's chemical based or even ion based, the lifespan of your rocket, if it's to maintain its orbit, is based upon how much thrust it can put out instantly, like what's its peak thrust. And then if you turn that on peak thrust, how long could it last? And then if it's a liquid fuel, what's the smallest amount you can use as a thrust? So you have these parameters associated with your propulsion capability. Liquid fuel is going to run out faster. You can think of it as when I watch a Falcon 9 launch, the first stage booster usually comes back in under 3 minutes. That's because at 3 minutes and 40 seconds, there's no fuel left. So that's why they usually come back to the pad or land out on a ship at sea in about 3 minutes. But you also know that there are deep space probes that have lasted for years. They're ion propulsion, and what they do is they run at about 11 to 14% of total thrust output for months at a time, and it adds up. This is how they go faster and faster and faster and faster and faster. And then when they get into orbit of something, they have to use their chemical rocket because it has a higher peak thrust to quickly slow the vehicle down to go into orbit. And then when they want to leave orbit, they use the fuel to kick it out of orbit, and then they use the ion thruster to take it to its next location. But how do they do that with like the big satellites? Well, if it's a critical satellite like a weather satellite that just always has to be there, what they'll do is they'll put them out with backups. So you might find like there's a GOES, GOES. When the GOES satellites go up there, a couple of years after one gets up there, they launch another one. And they put it into a parking orbit not too far from where it would normally be. So when they have a problem or it starts running towards low fuel, they take the active satellite and they shove it over to the Pacific, and they bring the other one in from the edge of the Pacific into that same station. So you have a replacement process for GOES satellites. And that's how they deal with it. Like, they do run out of fuel, and once they run out of fuel, they tend to drift plus and minus that station keeping orbit over the Pacific. So I read about recently, I saw on a video, there's a new approach. Instead of carrying your fuel from launch where you have a static supply, all that gas around you that's dragging you back, what if you had a big scoop and you compressed all that gas into a tank, and then as you needed fuel for propulsion, you would squirt some of it out, and then you would have a very high electrical charge, and you would accelerate the ions and use that for propulsion. So it's kind of like an ion or Hall effect propulsion engine, but instead of carrying your fuel from launch, you have a scoop to collect the gas, and then you ionize that. Sounds very much like the Bussard collectors of Star Trek Enterprise. Those giant blue swirly things on the front, those are called Bussard collectors. And what they're doing is they're using an electrical field to draw in all of the hydrogen that is in free space, and then they use the antimatter accelerators to accelerate the ions out the back at relativistic speeds. Now that's how they can get close to the speed of light. This wouldn't be anywhere near the speed of light. This will be just enough to keep it in its proper position and altitude to sustain the orbit. But you need a lot of electricity because it takes more electricity to accelerate oxygen and nitrogen than it takes to accelerate argon, xenon, or krypton. You need a lot of electricity, which you're back to the Achilles heel of now you got to have large solar panels to get the electricity. Well, why don't you just put a fission reactor or a radioisotope thermoelectric generator like they use on deep space probes on one of these very low Earth orbiting satellites? It was a Russian satellite that had nuclear power on board. It luckily, when it finally burned up, landed in Canada, but there's an area in Canada that's like a radiation no man's zone because when the satellite burned up, not all of it burned up, and when it finally did melt, it kind of like spewed the core of the reactor over an area. It's the radiation zone in Canada. But they monitor for that. They have public radiation detectors. So not a good idea to put RTGs or fission power in orbit because deorbit burnup may scatter radiation. So you're back to solar panels. How big can you make them so that the drag is not great? Well, turns out you need about 24 kilowatts for your atmospheric acceleration, but with the size of panels, they can only get to about 12 kilowatts, so they're a little low. But the propulsion output is still fractions of a Newton, just like it is for ion. But here's one they ran into recently. The Earth's atmosphere is bumpy. It's not spherical. So there are parts of the Earth where gravity is greater and lesser, and where it is, the atmosphere does bulge out or does indent in. And so if you're sucking in that thin atmosphere to use as your fuel, you may go over areas where no fuel to suck in. So when you get to the thicker areas, you have to suck the fuel in harder and concentrate it harder and store it in an onboard tank so that you can use that to spew out for acceleration the fuel that you're not going to get over the thinner atmosphere areas. But that means you now have to have a bigger tank on board. You need more electronics, more plumbing, more software for the electronics to switch it. Complication. And this was another one they found out recently, just this year. Metallic oxidization of the anode of the accelerator. So when you're trying to draw in the atmosphere, you need an electrical charge to act like a Bussard collector and suck in all the atmospheric particles. Well, you need a large electrical charge to do that. And even using a platinum tip, it's eventually going to oxidize. And so that's another Achilles heel on the lifespan of your satellite is, okay, you've got your electricity, you've got your fuel that you're sucking in, but your anode's going to oxidize and that's the end of your spacecraft. So maybe having a backup allows them to make it last longer, but Achilles heel after Achilles heel. But the one that they don't mention with ion propulsion that's really is its Achilles heel of fuel consumption is the grid, the acceleration grid. If you take the accelerated particles and you shoot them through the grid gets a charge on it. And therefore the molecules that are outside need to discharge the grid. Otherwise the grid charge gets too high and it is no longer as effective as accelerating molecules. So they have a spew that's out beyond the end of the nozzle on the egress of the accelerated particles that spews unaccelerated gas over the grid to discharge it. And that's a good portion of the fuel consumption beyond what it needs for propulsion is just discharge gas. So here's a different approach. Why don't we use radiation reflection pressure for the propulsion? Still only fractions of a Newton, just like ion and HALE, but use Casimir battery power cells for your power generation, maybe having smaller batteries and no solar cells. So you have no fuel tanks, no storage tanks, no valves, heaters, plumbing, and fittings. And if you use the latest technology of LED emitters or lasers, then you can get more photons output for the same space at lower power. So that would probably expand the lifespan to easily 5 years, but the technology has to be developed. But the same thing can be said for this atmospheric concentration, air ionization, and acceleration. Sometimes solutions that don't currently exist take work. So I found this one fascinating. What if you wanted to go even lower than orbiting? There are not really satellites that are long endurance vehicles. They're known as stations, just not space stations, or they're referred to as high altitude pseudo satellites. They're called high altitude long endurance vehicles, or HALE vehicles. These are suborbital, they're recoverable, they can land at airfields if you want them to, and they don't fall back to Earth or burn up. Military aircraft do this, like the Global Hawk. The Global Hawk has a flight time, a linger time approaching 1 month. So they can use them for environmental monitoring because they'll fly at an altitude well above any local weather. If you have a couple of them over an area, you can use them for law enforcement because you don't have to wait for the aircraft to be run up and take off and fly over to an area. They're up high enough where they can see like the entire city or the county. It's usually above 60,000 feet or about 11 miles, about 18 kilometers, still well within the atmosphere. If you fly them correctly, then they're either jet or propeller-driven uncrewed drones, big wings, or maybe airships or balloons that they can control their buoyancy. Their period of being aloft is usually a minimum of more than a day, but their goal is 1+ months. But if they're running anything, if it's an electric prop or a fuel burning prop or a jet turbine, you have a fixed fuel capacity when you take off, and you have to be able to maneuver around and fight wind currents. Maybe they should also consider other forms of propulsion. But they can use solar panels. So in conclusion, very low Earth orbit does exist, has several advantages: lower launch costs, increased orbits per day, low communications latency. The limiting factor is still the static fuel capacity, which is determined at launch. Some see for satellites ion or Hall effect propulsion as a solution, but it still has a fuel tank that eventually runs out. So atmospheric concentration can provide the fuel, but they've got component degradation and power generation issues to deal with. And remember, nuclear power is unacceptable due to the deorbit radiation risk. Large solar arrays for the power that they need would increase drag and reduce the orbital lifespan. They still need a solution. So maybe radiation reflection pressure for propulsion and Casimir effect power modules for power generation. They could also be used in these non-orbiting, high-altitude, long-duration sort of aircraft, but if they were using photonic propulsion, then they wouldn't need wings, because you still call them aircraft. And a bunch of links for each of the types of orbits, HALE aircraft, and for those that aren't familiar with it, radiation reflection pressure and Casimir effect for power generation. Comments, questions?
It's very interesting to know all that.
Well, I knew that.
The general public just thinks of satellites as all over the place.
Yes, and especially when they look at those lying to you pictures of the globe, it looks like the swarm of bees of satellites. If the Earth was really scaled down to that size, the satellites would not even be visible. And they're drawing a picture of a satellite that looks like it's the size of Germany. And there is no satellite up there that's the size of the nation of Germany.
Still, there's an awful lot.
Space is big.
Yeah.
Here's the simple math. If you take the diameter of the Earth, 4,000 miles, and then you say, my low Earth orbiting satellite is 250 miles up. Okay? Take that 250 miles, add that to the 4,000 miles, multiply by pi, and you'll get the circumference of the orbit. That's the ring that the satellite's roaming in. You'll see how many millions of miles that is for one orbit. And then you say, I can now take that orbit and I can tilt it, and they won't interfere with one another because they're on different angles. And then I can increase the orbital distance by 10 miles. And there's literally 10 miles separation between the satellites vertically, and there's about 200 miles separation horizontally. And that's just one layer of satellites. So you can have hundreds and hundreds of layers of satellites all the way out to geostationary before you ever think, I've got a lot of satellites. It just sounds like a big number. It intuitively says, if you've got 5,000 of them up there, what's the risk of them running into each other? Nil. Until people start blowing them up, or they explode, or they don't fully fall back to Earth, then you've got a problem. But remember, the very low Earth orbit is considered a self-cleaning oven.
Isn't there a concern, though, that this is all one company that's doing this, right? They're becoming like a nation unto themselves up there in the space. Even if it's a small country of Germany, it's a country. I'm just making a comment. That's it. Thank you.
I think you're confusing how I was referring to Germany. If you shrink the Earth down so it fits on your video screen from 4,000 miles down to, let's say, 6 inches, if you, by the same scale, shrink the satellites down to that same scale, you would not see a single satellite orbiting the Earth because they appear so small. They would be smaller than points.
Okay, but there's 5,000 of the same company up there.
Yes. They're not all all at the same altitude.
I'm not concerned about them running into each other. I'm just concerned that one company is out there.
That company is not a rogue. That company operates with the approvals of its orbits by both NASA and the FAA. And
okay, which I'm very happy about. However, what if they wanted to go rogue?
There is a nation out in the Pacific Ocean that does not operate under international guidelines for satellite orbits. They will profess not following the rules, but they actually do follow the rules because the orbits are all published. The US has this organization that still exists called NORAD that tracks everything in space from the size of a pea larger. So every one of those 5,000 satellites, the orbit is tracked and updated on a regular basis. So there may be a lot of them, but they're not operating as a rogue. But there is a nation that is operating as a rogue, but it still follows the rules. It just says publicly, we are under no obligation to follow those rules, but they do. Now, why is it that they wouldn't follow the rules? Because they're a Pacific Island nation and they're near the equator. So what is directly overhead for them as a viable communication satellite for TV broadcasting is a position where when satellites that are geostationary go end of life, countries like the US and Europe would like to park their dead satellites in those places. So they're not following the rules because they want a satellite directly over their nation, but you've got these other nations that are supposedly operating under the rules of law that want to park satellites over their nation. So who's the rogue? Well, it turns out when you park a dead satellite at a geostationary orbit over the Pacific, due to variations in the Earth's rotation versus the orbital period, the satellites don't sit still at the angle above Earth at that orbital position. They actually slip back and forth. And as they do that, that means the keep away zone over this island nation needs to be broader than just straight overhead. It needs to be several degrees plus or minus. And that eats up that parking space for the other nations to dispose of their satellites. You have to look at this stuff with a lot of minutia before you figure out who's actually the bad operators. And it turns out the company with the most satellites is actually not the bad operator. It's the organizations with the smallest number of satellites that don't owe any international allegiance to the rules that are identified as the ones to watch out for, or China, Russia, and the US as the bad operators when they go, we're just testing out weapons. We've got a dead satellite up there. We're going to shoot a missile at it and blow it up just to prove we can. Well, that was part of the Star Wars program. Star Wars, good thing, protects us, right? Okay, but you created a debris cloud. And when the debris goes out, it goes out in all directions, which means it goes to higher orbits, it goes to lower orbits, and it goes to all the same altitude orbits when that debris cloud fans out. So NORAD has to track all those pieces. And because Starlink has so many satellites in orbit, the satellites are given the privilege of a buffer zone. So if a satellite, which actually has its own radar, detects, hey, I just noticed something on my orbit that I could interact with, I'm going to slip myself left or right, up or down just a little bit, could be a half a mile in all the directions, to skip over or skip around that debris that was caused by some rogue nation like the US or China or Russia blowing up satellites. It's a big picture item. And I do not profess to chastise anybody that does not know about these things, because they change all the time. Nobody's born knowing this stuff. And because of the negative PR value of them, you're not going to hear about the mainstream media talking about these kinds of things. They'll just look at the success and go, hey, look, Star Wars worked. We blew up a satellite. Any problems with that? No. So then to prove they were on par with our technology, you had to have China and Russia doing the same thing. But they didn't blow up somebody else's satellite. They blew up their own satellite. Okay. Comments or questions before I stop recording?
The International Space Station is considered low Earth orbit, right?
Yes.
It's only a couple of 100 miles.
Yes, but it has a bigger buffer zone around it than communication satellites do. And the space station always has one or two Soyuz capsules docked with it.
Ready to go. Yeah.
No, not ready to go, ready to boost it out of the way. The space station itself does not have very high performance thrusting capability and has a limited fuel supply. So they have basically docking stations on the end, above, and below. And if they want to go up a little bit to avoid some debris,
They use those.
they get in the other Soyuz or a Dragon capsule, and then they autonomously control the other Soyuz capsule to boost the orbit a little bit or slip it one way or the other to get out of the debris field. And they'll talk about things like, if it gets closer than 50 miles from the station, they take this sort of action. Everybody get out of the station, go into one of the capsules, and then use the other capsule for navigating fuel. But they won't fire up the maneuvering Soyuz until it gets to like 25 miles. So at 50 miles, they just evacuate, move into a capsule in case their estimates are wrong. But if it gets within 20 miles, then they'll just boost it out of the way.
They've done that. They've changed its position.
Yes.
Right?
Well, they have to do that on a regular basis because at low Earth orbit, it's been up there for decades. There's enough molecules of atmosphere. It slows it down. So periodically they have to, have to boost it back up. And the space shuttle used to be used for that. So now they have to use the Soyuz capsules because the Dragon capsule does not carry enough fuel to do its deorbit burn and still have enough left over for occasionally kicking the space station around. But the Soyuz does. Now, if you look at the Dragon is like spacious on the inside. They have room for 4 easily and can add 2 more astronauts on the lower deck. That's the capsule. The Soyuz had room for three. That's it, room for three. And you're packed in there like sardines. Even tighter than the Apollo capsule was. So they've got more room for fuel. And if you ever look at the service module size difference between the Soyuz and the Dragon service module is on the back end. And it's mostly hollow for cargo. It carries unpressurized cargo. So we can carry like big stuff like solar panels and stuff like that rolled up in the cargo bay. The Soyuz, there's a limited amount of supply space, and it's kind of on the way out of the capsule. You'll see that there's a sphere, which is the capsule, and then there's another sphere on the front of it. That's like storage, and then the bigger service module with the propulsions on the back of it. So different designs. Minutia. I can't help it. I must learn the minutia. Okay, any other comments before I stop recording? Hearing nothing.